So if we look at a queue that is an MM1 queue, if you remember, MM1 means the arrivals are Markovian, meaning they have an average, but there's no connection between the last one and the next one. They come very independent of each other. And the server also is Markovian. So again, these are both Poisson processes. They can happen at random frequencies, but they all have an average. Since I didn't say this, the number of servers is 1, so the queue would look like this. I didn't say how many seats are in the queue, which means by default it's an infinitely long queue. I didn't say what the queuing discipline is, so by default we assume it's first come, first served. And we have a rate of lambda coming into the queue and a service time of mu, things being serviced. Okay. So the MM1 is almost the most common, if you look up on Google, the most commonly talked about queue, simplest queue is the MM1 queue. One server, queue is infinite, and the arrivals are Poisson and the service times are Poisson. Okay, so suppose we consider the states of a queue to be the number of processes in the queuing system at any given time. So suppose one process is being serviced and one is sitting in a queue. That would mean this queue is in state 2. Right? That's, the state is the number, and the number is how many processes are in the whole system. Queue plus server combined. Okay? So, what we like to eventually figure out is what percentage of the time are we in state 0? What percentage of the time are we in state 1, state 2, and so on, and then maybe take an average so we know on average what state are we in. And that'll translate into, when we arrive at this queue, on average, what do we expect to see in front of us? So, what is the probability that we are in state 0? Here's what I'm going to do. So, we could be in state 0, we can be in state 1, we can be in state 2. Since the queue is infinite, theoretically we could go out to state infinity. And this goes so on. So we're going to draw a little state machine. What percentage of the time are we in state 0? What is state 0? State 0 means nobody's in the queue. Nobody's being serviced. The queue is empty. We want to know what percentage of the time are we in all of the states. So what percentage of the time are we in state 0? So the utilization of the queue, we say, we use the Greek letter rho to say what percentage of the time is the server in use. And we said last time, for example, let's do an example. We have an MM1 queue with lambda equals 2 per second and mu equals 3 per second. What did that mean again? Processes are arriving at a rate of 2 per second. The server, the thing doing the work, if it was put at full capacity, it was running all the time, it moves at a speed of, it can output 3 per second. But it might not be in use all the time. So obviously, if 2 per second are coming in, 2 per second are going out, it doesn't create new processes. So as long as it can handle the workload, the rate in will always equal the rate out. But it's fast enough that it could actually, if it was working all the time, it could output 3 per second. So what percentage of the time is this thing not in use? So we said last class, rho, the percentage of time that the server is in use, we said that was equal to lambda over mu, which in this case would be 2 divided by 3. So 2/3 of the time this thing is in use, right? So the question is, what percentage of the time are we in state 0? This is the new question tonight. I'm going to say probability 0. If we arrive at this queue at a random time, what is the probability we are in state 0, meaning nothing is in the queue?
1 minus lambda.
1, yeah, right, yeah, perfect. 1 minus rho, which is really 1 minus lambda over mu. That's the percentage of time we are in state 0. Okay. Now, what percentage of the time are we in state 1? We're going to try to come up with a formula so we could do where 2, 3, 4, any value. Okay. So, how can we figure this one out? So we now know the percentage of time we're in state 0 is 1 minus the percentage of time something's going on. If we were to look at what rate do we go from state 0 to state 1, that would have to be equal to what? So, let me think of an analogy. Suppose you have an elevator that starts off in the morning on the ground floor, and it's going up and down in a building. And you ask yourself, how many times a day does it go from floor 10 to floor 11? It doesn't have to stop at every stop, but if it goes from 10 to 11, what's the frequency? How often does that happen per day? Would it be exactly equal to how often it goes from 11 to 10? Every time it goes, like, you know what I mean? I'm not saying you have to stop at every floor, but every time the elevator goes in the direction from 10 to 11, let's say that happens 50 times a day. How many times did it go from 11 to 10? 50, right? Assuming the elevator ended the day down at the ground floor. It could be 49 if it got stuck at the roof. But the number of times you go from state 0 to state 1 would exactly equal the number of times we went from state 1 to state 0, assuming we started at 0, let it run all day, and then ended at 0. They would equal each other. So what is the rate? How often do we go from state 0 to state 1? How many times a day, or per unit of time, do we go from state 0 to state 1? Well, we'd like to know what percentage of the time are we in state 0. And then if we're in state 0, what has to happen to go to state 1? What event would need to happen? A process would need to arrive to our queue. Then we would go from state 0 to state 1. We're going to call that a birth. One thing got added to our population. So if we go from state 0 to state 1, and an arrival showed up, or a birth showed up, so what rate does that happen? Well, the arrivals are coming all day long at a rate of lambda. But if we were in state 4 and then arrival came, we'd go from state 4 to state 5. We only want to focus on going from state 0 to state 1. So what rate are we going, not from any number to the next highest number, but what rate do we go from state 0 to state 1? It wouldn't be lambda. Lambda is the rate that we go from some number to the next highest number. Right? 2 times per second, we go from some number to the next highest number. Could be from 4 to 5, could be from 0 to 1. But 2 times a day, if lambda was, like in this example, 2 per second, then 2 times per second, we are going from some number to the next highest number, right? So if the first question, an easy question would be, how often do we go from one state to the next highest state? That would be 2 times per second. right? Because 2 times per second something shows up. It's a bird every two times per second. So the rate at which we go from some number to the next highest number is 2 per second. But here's a different question. What is the rate that we go from 0 to 1? How often does that happen? Is that 2 times per second? It's less than that, right? How much less?
Depends on what n is.
Well, what if I told you that the percentage of time we are in state 0 is 1/3. 1/3 of the time we're in state 0, 2/3 of the time we're in some other state. What is the rate that we go from state 0 to state 1? It would be not 2 per second, but 1/3 of 2 per second. It would be, in this example, the rate that we're going from 0 to 1, state 0 to state 1 would be 2 per second divided by 3. So 2 would be 2/3 per second. Because it's the amount of time we're in the state and then an arrival comes. If we were in the state of 0 100% of the time, for that to happen, this thing would have to serve everything instantaneously. Then we'd be constant, every time something arrived, we'd be going from 0 to 1, because the queue would immediately go back to 0. Let's say it instantly went back to 0. Then we would be constantly in state 0, which means we'd be going from state 0 to state 1 2 times per second. But we're only in state 0 1/3 of the time, so it's really 2/3 per second. Not 2 times per second, but 1/3 of that value, 2/3 per second, is the rate at which we go from state 0 to state 1. Now, like we said with the elevator, if the rate at which you go from the 10th floor to the 11th is 100 times a day, then the rate you're going from the 11th floor to the 10th floor has to be 100 times a day. Every time it goes up, it comes down. So the rate at which we go from state 0 to state 1 is lambda times the percentage of time you're in state in state 0. What is the rate at which we go from state 1 back to state 0? So how do we go from state 1 to state 0? Well, we're serving somebody and nobody's in the queue. That means we're in state 1. And then the server says, okay, I'm done with this guy. So we went from state 1 back to state 0. So the rate at which we go back is whatever mu is. So the percentage of time that we are in state 0 times lambda, that's the rate at which we go from 0 to 1. The percentage of time we're in state 1 times mu, that's the rate at which we go from state 1 back to state 0. Those should be equal to each other. So, mu times the probability we're in state 1 should equal lambda times the probability we're in state 0. What we're really saying there is, like, the elevator going from the 10th to the 11th floor happens just as often as the elevator goes from the 11th to the 10th. The rate at which we go from state 0 to state 1 is the percentage of time we're in state 0 times lambda. That has to be exactly equal to the rate at which we go from state 1 back to state 0. If it happened 15 times an hour, then we go from 1 back to 0 15 times an hour. They have to equal each other. So another way of saying this would be the probability we're in state 1 is equal to lambda divided by mu times the probability we're at state 0. Okay, now for an MM1 queue, it'll be different if we added more servers and we changed the queuing around, but for an MM1 queue, how often do we go from state 1 to state 2? Well, and how often do we go from state 2 back to state 1? Well, if we're in state 1, that means there's something in the queue, there's something being served, but nothing's in the queue. What has to happen for us to go to state 2? An arrival has to come. Another bird has to come. That has a rate of lambda. So to go from state 1 to state 2, if we said to ourselves, how often does that happen? Well, it's the percentage of time we're in state 1 times the rate at which we increase to the next state. So that would be, so this is a true statement. And then the probability we're in state 2 times mu equals the probability we're in state 1 times lambda. The rate at which we go from state 1 to state 2 has to equal the rate at which we go from state 2 to state 1. So, said another way, probability we're in state 2, or percentage of time we're in state 2, would be equal to lambda divided by mu times the probability we're in state 1. Probability we're in state 1 is lambda divided by mu times the probability we're in state 0. So this would end up being lambda divided by mu squared times the probability we're in state 0. And for the Mn1 this just goes up, this can go out to infinity. So the probability we're in any particular state, I, is equal to lambda over mu, which is the utilization, raised to the I, times the probability we're in state 0. That makes sense? So let's do an example. Let's use this example. We have an Mn1Q. The rate coming into the queue is 2 per second. The rate, if fully utilized, going out is 3 per second. What is the probability we are in state 0? Probability we're in state 0, we said before, was 1/3. So that was 1 minus rho, which is 1 minus 2/3. 1 minus the amount of time this thing is in use, whether they're stuck in the queue or not. The amount of time this thing is in use is 2/3. So 1 minus that equals 1/3. What is the probability we are in state 1? If you show up at this queue at a random point in time, what's the probability you are in state 1? That would be lambda divided by mu times P0. So that would be 2/3 times 1/3 equals 2/9. Probability we're in state 2 would be 2/3 squared time, and then at the end times it by 1/3. This would be 4/27. And it makes sense that this goes on to infinity. It is possible we could be at state 100. It will probably happen a very low percentage of the time. But it could happen, right? So 33% of the time we're in state 0. The thing's not being used. 2/9 of the time we're in state 1. There's somebody here but nobody in the queue. State 2 would be 1 process is being served and exactly 1 is in the queue. That's state 2. We're in that state 4/27, so approximately 16% of the time we're in state 2. This is like 23% of the time, so it's something like 33, 23. Oh, wait. No. 2/9 is, yeah, a little over 20, 22. 4/27, 16, around 15% it says. Anyone has a calculator, but as long as that's close. And as you can imagine, the less likely ones, as it gets bigger and bigger, it's still possible, but those percentages will drop. So that, we can go on and on doing this. Okay, so basically we have a formula for the probability of being in any one of the states. The state is the actual number of processes in the system, and that's what we're looking for. We want to know when we arrive at this queue, on average, what do we expect to see in front of us? So, how do you figure out an average? How do you figure out an expected value? So suppose we had an expected value like, what is the expected value of rolling a dice? How do you solve this problem? So if you roll the dice, what is the expected value, the outcome of the dice roll? The dice can come out 1, 2, 3, 4, 5, 6, each having a 1/6 chance.
N factorial.
What's that?
N factorial.
N factorial?
N times it can be 1.
No, if you roll the dice, what would you expect it to come out to be? So for example, if you had if there was some event that either came at half the time it came out of 1 and half the time it came out of 2, if I said what's the expected value, it would be 1.5, right? So, and now you'd never see a 1.5, but that would be the expected value if you ran it many times. So what would be the expected value of the dice?
3.5.
3, what?
3.5.
Yeah, 3.5. But how would you calculate it? Like in a probability class, what would you do?
Sum of.
You'd say you'd sum up from I equals 1 to 6. You would sum up the value times the probability that value will be hit. So that would be 1 times 1/6 plus 2 times 1/6 plus up to 6 times 1/6. So there's a 1/6 chance you get a 1. So we had a 6 plus 2 6 plus 3 6. So this is going to be 1/6 plus 2 6 plus 3 6 plus 4 6 plus 5 6 plus 6 6. Add it all up and it equals 3.5. That's what you would expect. So if you have an event, if you have some random event that's occurring and you want to know what is the expected value, you would take the probability that the event will happen times the value and just add it all up. And that will come out to 3.5. So, alright, so that's an example from probability class. Okay. Now suppose we have the queuing problem, the MM1 queue we just had. So suppose we arrive at the queue, we say, what is the expected number of things in front of us? How do we calculate that? So, example 2, MM1 queue. What do we expect to see in front of us? The expected value, I'll just say the value is X, equals, we want to sum up. Now, it's going to go to infinity. It's not like a dice that goes from 1 to 6.
It's going to be I equals P0 to N.
I can equal, we can be in state 0, and we can actually theoretically go off to state infinity.
Right.
So this looks like it's going to be harder than the dice problem. Times I times the probability of I happening. That's what we were just calculating before. What is the probability of I happening? So it ends up being the sum from I equals 0 to infinity. I, the probability it would happen was what? It was this formula. Lambda over mu times P0. Lambda over mu to the I times P0. Okay. Still looks complicated. P0 is a constant which we can move out. anything that's a constant in the summation. If you do some formula +4, and every term is a +4, you could just multiply the whole answer by 4. You could pull a term out, like we did here. There's a famous mathematical identity which says that the sum from I equals 0 to infinity of I times something, let's say alpha, to the I minus 1. Does this ring a bell from calculus 2? Maybe calculus 1, limits that, remember when you're studying limits, then all of a sudden there was some series that if you added it up to infinity, it would come out to a certain number. There's a kind of like a page or two in your calculus book that said this was equal to, what was it equal to? 1 over 1 minus alpha squared. Is that right? Yeah. So this comes from the limits part of your calculus, of course. Okay. And this would be nice. This sum to infinity is a problem. We'd like to get rid of that. So what we can do is we can say this is equal to, now what we're trying to do is we're trying to take the lambda over mu and substitute that in for this alpha. But the problem is we have an I here, so we'd like it to be an I minus 1, and then we'll go. So this equals P0. We'll pull out one copy of lambda over mu, and then we'll sum up I equals 0 to infinity of I times lambda over mu to the I minus 1. That's the same thing as that. All I'm trying to do is I'm trying to take this formula and use this identity from mathematics class. This now, so what are we doing? We're trying to figure out the expected number of things in the queue in front of us when we run. That was the whole point from the beginning. Now we're playing around with calculus, some results from calculus, but what we have is this is equal to P0 times lambda over mu. This whole thing now here becomes now, P0, so we need a separate effect. We'll use it for pen. P0 we said before, P0 was equal to 1 minus lambda over mu. Right? We said this before. The time when state 0 is the 1 minus the time the server is in use. Okay? So with that being true, this becomes 1 minus lambda over mu. So I'm just putting in P0 here, times lambda over mu, times 1 over 1 minus lambda over mu squared. We can cancel this and this to get lambda over mu divided by 1 minus lambda over mu. So we basically took from probability, we took the idea that we're trying to figure out an average, figure out what is the outcome and the probability of that outcome happening, sum it all up, and that's your expected value. In this case, these states actually went off to infinity. So it's not like a dice where you count up to 6 and we're done. This actually went off to infinity, which looks like it would be like an intractable problem. We'd never be able to solve it. But instead, we were able to use this math identity and play around with the fraction a little bit to get from this step to this step. Once we got here, we were able to get rid of the summation off to infinity and come up with concrete values. So in the example with lambda equal to, an example with an MM1Q with lambda equals 2 and mu equals 3. When we arrive at this Q, how many processes do we expect to see in front of us? It would be, the expected value in front of us would be 2/3 divided by 1 minus 2/3, which would equal 2/3 divided by 1/3 is 2. So we're going to arrive at this Q, 1/3 of the time it's going to be empty. We're going to go right in and get served. What else was there? 33% of the time the queue is going to be empty. 22% of the time there's going to be one customer in front of us. 15% of the time there'll be two in front of us. Then if this kept going, it'd be 10% of the time with 3. And it would get lower and lower, and it actually goes off to infinity. If you said, what is the probability there'll be 50 in front of us, there's going to be some number. It's greater than 0. It would be, what was the formula again? It would be 2/3 raised to the 50, which would get pretty close to 0 times 1/3. But it's still a chance, there's 50 in front of us. But on average, out of all the possibilities, on average, we can expect to see 2 in front of us, on average. Sometimes it's going to be less, sometimes more. On average, it's going to be 2. So when we arrive at this Q, how much time will it take for us from the moment we arrive to the moment we leave the Q? How long would that take? So the expected wait time, I think we use W, the wait time for service would be the 2 in front of us plus us. We have to be served too. And at what rate does this server service at? It services at a rate of 3 per second. So the numbers were all set up to make the math really easy. So when we arrive at this Q, we expect to see, on average, 2 customers in front of us. And assuming it's first come, first served, they have to be served before us. Then we get served. So really 3 services have to happen before we're done. The 2 in front of us plus us. And it turns out the server serves at a speed of 3 per second. So we will take a total of 1 second to get through this queue. 2 seconds is us sitting in the queue waiting to be served, and 2/3 of a second is us sitting in the queue while someone in front of us is going, and 1/3 of a second is us going. So you add the 3/3, and it adds up to 1 full second for us to be done. Okay? So now if we wanted to go over an example where, if let's say we had a system like this, a queuing system where we'll have a network of queues. Suppose we had a processor with a queue in front of it. And 20% of the time, we go to one disk drive. We'll call it disk drive 1. %10 of the time, we go to disk drive 2. And after the page fault, let's say we're processing, we hit a page fault, and that sends us out to one of the disk drives. After we get the page back, we go back into the queue again. And same thing true if we went to disk 2. Then let's say 10% of the time, we exit the system. And we are entering this system, jobs are entering the system at, let's say, lambda equals 1 per second. And let's also say that sometimes we go to the processor, we're at the processor, and we run for a while. We don't have any page faults, we just time out. Right? The operating system lets everyone run for a certain amount of time and then says, okay, time's up. You go back to the ready queue, and then you can run again. So let's say the operating system is keeping statistics on when you depart from the CPU. And it notices every process that visits the CPU, 20% of the time it goes out to disk 1 looking for a page. 10% of the time it goes out to disk 2 looking for a page, and then once that page comes in, it goes back to the ready queue. 10% of the time, it's done. It executes its last line and it's done. And then the remaining, what's the remaining? 60% of the time. It runs for a little while and the operating system times it out and says, okay, get back to the ready queue. Someone else needs to go. If we wanted to know how long does it take from when our process starts until our process finishes, on average, how would we add that up? We could, is there a couple ways to do this? We could say to ourselves, how many times do we go to the CPU? How many times do we go to disk 1? How many times do we go to the disk 2? How much stuff is in front of us? How much time does each visit take times the number of visits and add it all up? Right? So we need some mu's. Let me make up some mu's. The mu of the CPU will be 20 per second. The rate is 1%. The mu of disk 1 will equal 5 per second. The mu of disk 2 will say 2 per second. Now, why would one disk be slower than the other? Well, maybe the files on here are sequential files, and maybe the files here are indexed, so you have to look at an index and then run all over the disk drive looking for the file. For whatever reason, the operating system noticed that this disk drive is moving a lot faster than this one. Okay, so with some mu's, now the question is, the lambda into the overall system, the rate into the system, 1 job per second is entering the system. What is the rate into the CPU? Is it 1 per second? Or is it more than 1 per second? It's going to end up being more than 1 per second because the outside world is sending them in 1 per second. But the jobs in here, 90% of the time, come bouncing back to here. Right? So it's going to actually be a much higher rate. So what is lambda CPU? And we did this one last class. We said the expected number of times that a job will visit the CPU, the expected number, we did something like this. The expected number equals 1, because as soon as you come in, you have to visit it at least once. And then 90% of the time, you'll visit it again. So 90% of the time, you'll visit it again. And this would say the expected number of visits of the CPU would be 10. And we did that last time. The number of times you'll visit the CPU will be 1. It's definitely 1, because the first thing you do is visit the CPU. It'll definitely be 1. and then 90% of the time you go back to the beginning. So whatever E is, that's the number of expected visits. It'll be 1 plus 90% of whatever E was, which became 10. What?
You've got 90%, which is 0.9.
Right, yeah, 0.9. So, okay, so this would end up being, if we subtracted 0.9 from both sides, we would end up with 0.1 E equals 1, which means E equals 1 divided by 0.1, which is 10. So actually, for every time you come in from the outside world, there's on average 9 more visits, a total of 10 visits for every process that comes in. So lambda of the CPU, was 10. Lambda of the outside world is 1, lambda of the CPU is 10 times higher. Now, since the CPU happens to feed these two cubes, what is lambda of this one? 20% of everything that comes into the CPU goes that way. So we could just take 20% of this number. So that would be 2. Lambda of this 2 would be 1. Okay. So we know the lambdas, and I just made up some u's. So the number of visits, and again, I made the numbers work out good. We're going to visit the CPU 10 times on average. We're going to visit this drive 1 2 times on average before we leave. We might visit it more, might visit this 8 times, but on average we'll visit it 2 times before we're done. We're going to on average visit this 1 time before we're done. And these are the rates into those queues. So how much time do we spend at each of those 3 devices? So let me say time. How much time do we spend for each visit? That was, what did we say that was? Lambda over mu minus 1 over lambda over mu. So it would be 10 over 20 divided by 1 minus 10 over 20 plus 1 for us times the rate. Right, so what would we, when we visit the CPU, jobs are coming into the CPU at a rate of 10 per second. The CPU can handle them at a rate of 20 per second. So that would be 10 over 20 divided by 1 minus 10 over 20. That would be a half divided by a half. We would on average expect to see 1 customer in front of us. Sometimes 0, sometimes 8, but on average it will be 1 in front of us. And then plus us, a total of 2 things have to be served. So it ends up being 1 plus 1 times 20 per second. So that would be divided by 20. So we would expect to take 1/10 of a second. 2 divided by 20. Yeah. On average, when we visit the CPU, we expect to see 1 person in front of us. They have to be served, then we have to be served. So 2 things have to be served, and this thing can serve at a speed of 20 per second. So it will take us 1/10 of a second to be completely done. 1/20th of a second for the customer in front of us, and 1/20th of a second for us. Okay, now, we're going to, each time we visit the disk drive 1, what is happening? The lambda is 2, and the rate is 5, so that would be 2/5 divided by 1 minus 2/5 equals 2/3. 2/5 divided by 3/5 is 2/3. We would expect to see 2/3 of a customer in front of us. So it's like dice with 3.5 is the average. You'll never actually roll the dice and see a 3.5, but that's what you'd expect. So we expect to see 2/3 of a customer in front of us. So how long will it take for us to be done? It'll be 2/3 plus us plus 1 times, and it can do 5 per Hope I'm doing the math right. So we expect to spend 1/3 of a second there. There's 2/3 of a customer in front of us, and then plus us. So there's 5/3 total work to be done, and this could do at a rate of 5 per second. So that should be 1/3 of a second. And then the third one, same thing, would be, what do we expect to see in front of us? The rate in is 1 per second. The speed is 2 per second, so 1/2 divided by 1 minus 1/2 equals 1/2 divided by 1/2 is 1. We expect to see one customer in front of us, plus us. 2 customers, it can handle 2 per second, so we expect to take 1 second there. 1 plus 1 divided by 2. So each time we visit the CPU, we'd expect to take 1/10 of a second per visit. Each time we visit this one, 1/3 of a second. Each time we visit this two, 1 second. How many times do we visit them? 10, 2, and 1. So the total time would be 10 times 1/10 plus 2 times 1/3 plus 1 visit times 1 second. 1 times 1 would be 1 second. So we're going to spend a total of 1 second at the CPU. 10 visits, each one taking 1/10 of a second. 2 visits to disk drive 1, each taking 1/3 of a second. 1 visit to disk drive 2, each visit taking 1 second. Add it all up is what? 1 plus 2/3 plus 1 equals 2 2/3. Assuming I did the math right. So this would take us 2 2/3 seconds to get through this whole system.